Hello and welcome to the AVS e-talk, linking dry corrosion and catalysis, can surface chemistry influence corrosion pathways. Today our presenter is Petra Ranke. She's a professor at the Materials Science and Engineering Department at University of Virginia. This is a 1-hour e-talk on the topic, and we'll be starting here after we go through a few slides of introduction, and then we'll bring Petra in to begin. Our event sponsor today is Hayden Analytical. We want to thank them for their sponsorship for this event. And when you logged in, you are automatically muted upon logging in. This is a 1-hour presentation with no breaks, so we hope you have your coffee and something to eat with you. In advance of today's presentation, you had the option to submit a question in advance for Petra. She will likely answer those questions via email to get some more information from you. However, you do have the option to use the Q&A feature at the bottom of your screen today to type in any additional questions regarding today's material. So go ahead and feel free to find that now at the bottom of your screen, and she'll answer questions at the end of the talk. I do want to remind people that we have a couple of disclaimers regarding the presentation. We believe all the information is reliable and we are not endorsing any products. We have our copyright notification that this e-talk is being presented with the permission of the authors and instructors who obtain copyright releases, et cetera, et cetera. So please just be aware of these as we start today. I want to follow up with some online training events that we have coming up. We have an online short course program coming up in February of 2022. We have 6 courses on various topics. Registration is open for all of these now. So if you want to register in advance, you can do that. If you want to celebrate and ring in the new year, you can register in January as well. We have an e-talk in March of 2022 on measuring your level of vacuum, a guide to gauge technology. That'll be coming up towards the end of the first quarter. Registration will be opening soon. I'm just setting that up. And we have a couple of webinars to kick off 2022, one in January on fundamental and practical insights on stress evolution during thin film growth, and another one in February on atomic layer deposition from an applications perspective. Both of those are open for registration now, so be sure to check those out. We have a couple of technical meetings. These are just our spring meetings so far, March through June. We do have more available on the AVS events calendar. But you'll notice we have in March, the Frontiers of Characterization and Metrology for Nanoelectronics in Monterey, the Area Selective Deposition Workshop in San Francisco in April, the International Conference on Metallurgical Coatings and Thin Films in May in San Diego, and ALD, ALE in June. This is an international conference in Ghent, Belgium. We hope to see everybody in person at these events, so check them out. Their websites are up and running, and we'll hope to see you then. If you're not currently a member, AVS membership is good for 365 days. Prices are great. You can give yourself the gift of membership or give it to somebody else. It gives you access to publications, professional career development, technical resources, and discounts on registration for the before mentioned events. So check it out. avs.org is the website. Angela Klink is our member services administrator. She'd be happy to help you. For those who are students, don't forget we have student membership rates, student chapters, career services, and ways to get involved with AVS. And after today's presentation, I want to remind you to complete the online evaluation form. We appreciate any input, feedback, and comments related to today's webinar or e-talk. And at this time, I'd like to introduce Petra Ranke on linking dry corrosion and catalysis, can surface chemistry influence corrosion pathways. Petra, if you'd like to share your screen, I'll let you take over. And if you unmute yourself as well.
Yes, I am doing that right now. Thank you very much for the introduction. You should be able to see my screen now. Is everything all right?
You are all set.
Perfect. And thank you very much for the introduction. And thank you to everybody who's joining me today. I hope we'll get some good discussions going about the really, really complex topic of corrosion and oxidation. And since we're AVS, I think linking that to surface processes and hopefully to catalysis and some chemical aspects is kind of one of my goals today. If you send me a question when you registered. I think some of them will be answered during the talk because it's already built in the flow of the presentation, and all others I will certainly contact you by email and make sure that that you get that answer, or maybe I don't know the answer, and then I'll also let you know. Okay, welcome. Let's get started. One of the real challenges in corrosion is the question, what is really the problem? What do we want to know? And let me kind of preface that by the fact that I'm not only very marginally going to talk about aqueous corrosion. Today, it's really focused on the dry corrosion aspects, but a lot of the ideas, a lot of the way to think about the surface reactions can be translated to aqueous corrosion. It's just very different chemically driven and electrical field driven processes which play out in that realm. So you kind of just make it even more complicated and difficult if you go to, apologies, aqueous systems. So let me illustrate the problem. So corrosion itself is expensive. It's not expensive only on a local way. It's really expensive on a very global scale. Most structures, small and large, from bridges to electronic devices, are prone to failure. And they're prone to failure not just because the bulk material fails, which can always also happen, but it's also prone to failure because they corrode at the surface, which just limits the functionality over time. So if we want to use something for an extended period of time, we don't just need to get a grip on how they function as a bulk material, but we also need to get a grip on corrosion and find ways to mitigate that super expensive and sometimes even dangerous problem. Ideally, corrosion and protection from corrosion or degradation is built into alloy design, but that's a really, really difficult problem because the bulk properties and those of an alloy which give you the corrosion protection are not the same thing. So you have to find your margin, your little sliver of composition or surface treatment, which give you that window into also having corrosion protection. So for that reason, it's actually really important to understand what happens during the corrosion on a mechanistic perspective, so you can start to integrate that and have a much better idea as to how you can model and predict corrosion protection. One thing which also is becoming, I think, more and more important is to also integrate considerations of sustainability, which I think will change the game in the near and hopefully far future. As I said already, this presentation focuses on the dry corrosion, which is what I know best. However, we also have published some work with similar trains of thought in aqueous corrosion with a colleague of mine who knows the aqueous part much, much better. So if you think corrosion, the traditional way to think about it is, okay, we need to make an oxide or nitride or another layer on the surface which mitigates the detrimental attack to the alloy of whatever chemical environment my material experiences. So in general, if you work in air or in aqueous environments, this will be an oxide. So we'll also focus on the oxides. In general, that should be a dense oxide. So the best candidates are always chromia, alumina, and sometimes silicon dioxide. Those are dense alloys which don't dissolve well, but all of them at some point will volatilize. So if you go to very high temperatures, your conditions, your boundary conditions change again. So if you look at what you actually are studying in this context, you can see that it's a system which has many, many, many interfaces and surfaces. So this is a very schematic view, which has a tenuous relation to reality. But you have an oxide, which can have different oxides, which can have layered oxides. They're interlinked. You can have dual scales. So there are a lot of thermodynamically driven and kinetically driven reaction pathways, which can lead to really, really complex structures compositionally as well as crystallographically in the oxide. You have surface reactions at the oxide. You have oxide-oxide interfaces. You have alloy oxide interfaces, which is this one here. Let me get my nice laser pointer, which is kind of this part here. You have surface reactions at the alloy when you start off with the process. You have something which is alloy microstructure, which is the catch-all for you have grain boundaries, different grains, different compositions in the grains. And just to give you an idea, this is an example for these polycrystalline nickel chromium alloys, which we also study in our work. And you can see the grain boundaries, you see the grain shapes. So microstructure is generally not considered in most surface science studies, but it can have a significant impact of the corrosion performance. And one reason for that is that your transport of reactants plays a role. And that's not just, if we just think about single crystals, that transport is just on one very well-defined, meticulously prepared surface. In the real world, the transport of reactants in the alloy as well as through the oxide plays a significant role and is coupled to the processes which play out at the surfaces and interfaces. There are more and more studies coming up, which is partially because the analytical techniques have really, really advanced in the last decade or two. And the other thing is that people realize that looking at the interfaces, the very first steps of oxidation is actually important to model, predict, design, as well as understand mechanistically how you set the stage for forming a thick protective oxide. Okay, let me take the next step. What we are looking at is nickel-based superalloys. They have great mechanical properties. They have a high corrosion resistance in aggressive media like salt water. It should give you a hint because for a lot of this project, we've been funded by the Office of Naval Research. There's the connection to the saltwater part. And one thing which is very well known and has been studied extensively is the fact that just adding to nickel chromium a sprinkle of molybdenum or tungsten as a minor alloying element really suppresses pitting events. And a pitting event is a catastrophic breakdown of your oxide. We have an incredibly complex parameter space: alloy composition, pressure, temperature, gas composition, crystallographic orientation. And I'm absolutely certain I have forgotten a few of them. And within that complex parameter space, in our work, we have looked at a relatively narrow slice of that. And the reason for that is that if you have nickel chromium, nickel and chromium oxidation compete. Thermodynamically, they should not. You should never see nickel oxide. But if you're under conditions like 500-600 Celsius, maybe below, maybe an alloy which doesn't have a very high chromium concentration, you have a competition between the two. So the question is, how does that competition play out? Because that gives us important ideas on how to control really and push the oxidation process in one or the other direction. So generally above 700 Celsius, chromium will dominate because you have much more diffusion in the alloy, so you can't get to the thermodynamically preferred situation. You also need roughly about 15% of chromium in the alloy to get to that point. So the question is, what happens if we are not at high temperature and if we don't have an extremely chromium-rich alloy? Let me point out, chromium is really expensive. So you want to have like very, very little in the alloy. And the other thing, its mechanical properties are not great if you add more and more chromium. So that's the interplay between what you want to have from the bulk material and what you need in order to have a protective oxide. So how does it play out? And this is just a very general idea. This is valid for pretty much all the thermal oxidation processes. So you start from a blank alloy, just like on this side. Then you start to accumulate oxide on the surface. At some point you have a closed oxide, but you have a kinetics, which is called Cabrera-Mott kinetics, and I'll show you in a second what that means. And then if you continue to grow, your kinetics change, and you have something which is called Wagner type growth, where you get these thick, really thick oxide layers, which have nickel oxide and chromia and spinels, and they look kind of very inhomogeneous here also. So Wagner growth is driven just by the diffusion, the chemical potential gradient in the diffusion. While Cabrera-Mott, which I show here, is driven by an electrostatic effect, which comes, you build up a potential, you have your metal on the left-hand side, you have oxygen, which absorbs on the surface of this ultra-thin oxide layer. And because of that, you can equilibrate your Fermi levels, Fermi level in the metal to the highest occupied orbital of your oxygen species. And when they align, you have a contact potential. It's like in a diode, essentially. And you have an electric field which builds up. And that electric field drives the continued growth of your oxide layer and transport and supports the transport of your reactants through the oxide layer. So this is the so-called Mott potential. It's generally assumed to be this benign potential, and it's homogeneous, and it looks like an ideal diode. You get a step away from that idea. It is not like that, and I'll show you an example where you can very clearly see that this idea about this ideal Mott potential does not play out in reality. However, where we play our playground, and this is AVS, you want to look at surfaces and interfaces and all of that, is actually what's shown on the right-hand side. So we look at the moment when our oxygen adsorbs at the surface, oxygen radical diffusion, you have surface reconstruction, surface oxide, nucleation of the bulk type structurally oxide, and then we move into that Cabrera-Mott regime, at which point we're not as interested anymore. So we want to link between the clean alloy surface to the traditional growth regimes described by Cabrera-Mott regime kinetics. We also want to understand how that initial step, what happens early on in the process, actually influences whatever happens in the next steps of the oxidation. And trust me, that's a really, really difficult problem. So we hope we'll have work to motivate us for another decade. Apologies. So the other question we are asking in our work here is, if we add this minor alloying element, what actually happens? What does that change in my oxidation process? And these are questions which are big questions. So we are not the only ones working on that. And there are a host of different alloys which are of interest. So here, these are just snippets from the very recent literature. If you did work in this area and it didn't put you on that slide, please don't worry about that. This is just my personal selection right now at this point in time. So people look at nickel-based superalloys, aqueous corrosion, with surface science techniques like XPS. There are discussions about the origin of nanoscale heterogeneity on stainless steel, which was an STM study. The question of high temperature oxidation, which is shown here, it's in the Porando study, or the question what is different if you use oxygen or if you use water in the oxidation process, which, you know, things are unfortunately very, very different if you use steam or anything like that in the process. You can see that my selection is highly biased towards surface techniques, XPS and STM. And the reason for that is that's what we do, that's what we know best. So what I'm going to do now is I kind of pick several aspects of our work on nickel chromium alloys with very specific answers which apply to these alloys. However, they're really embedded in this question about generalizing from these experiments to how does corrosion happen? Can we develop rules which allow us in the end to design more corrosion resistant alloys or more corrosion resistant coatings on these alloys? So that's really our task here. And looking at the mechanism in details also gives our colleagues who do computational work, who do DFT calculations or molecular dynamics calculations of the corrosion process, this work gives them a handle on how to think and build up their models. And ideally that helps us to jump across different material systems and study them. Okay, so the methods I'm using, and I hope I don't have to introduce them in as much detail. I hope most of you have at least an idea how they work, is a scanning tunneling microscopy, which gives us a very detailed nanoscale view of the starting point. We use X-ray photoelectron spectroscopy, both as a laboratory, as a synchrotron work. And in this talk, I'll mostly show you work which is done at Brookhaven National Laboratory, the Beamland with Ira Valuyo and Adrian Hunt, ambient pressure XPS experiment, which introduced also a timeline as to the progression of the oxidation. We work at low base pressures because chromium is really, really, really sensitive animal. So we don't want to start our process being biased already. And the other problem is if you do a surface science experiment, you generally want to start with something which is clean, crystallographically well designed, can be prepared in vacuum to give you that clean, pristine sample, which you know extremely well. When we do that for the nickel chromium, because we want to change composition in our alloy and look at the reaction and the corrosion response as a function of alloy composition, having 6 or 7 or 8 single crystals is just not feasible. So for the STM work, we essentially grow a thin film of nickel chromium, and then we observe that thin film. We grow it on MgO substrates, and I focus today on the 100 surface. We also have data for the 111 surface if you're interested, which actually shows that crystallographic orientation is a significant aspect, which is generally not looked at because the majority of technical alloys studied is polycrystalline, like the microstructure I showed you a few minutes ago. We also use bulk samples, which are polycrystalline, essentially a randomized surface orientation, some with small, some with really, really large grains, with various compositions. And these alloys were cast by our colleague at the University of Wisconsin, Professor Perry Pascoe, who is an excellent metallurgist. Okay, let me start. This is a layout of all the experiments we have done. We've published some of them, not all of them. If you're interested in something specific which hasn't been published yet, just send me an email and I will give you, I will let you know what we learned from these particular experiments. So what I'm going to show you today is some scanning telling microscopy experiments and the ambient pressure experiments. The STM experiments show you what is different between nickel and nickel chromium, what changes, how do these two oxides compete. And the other experiments kind of hone in to the difference between binary and the ternary alloys. Okay, and first rule of surfaces, know your surface. Structurally, we are very well defined on our thin films. Compositionally is a very, very different problem. So nickel chromium is a random solid solution. FCC alloy, we're in the composition range where we should have a random solid solution. You can have surface segregation, which we have seen. You can have nanofaceting, which does not happen on the 100 surface. However, the question is, if you look at a random solid solution and we can't distinguish between nickel and chromium, so how does that look like? And that's what this graph kind of shows you. It shows you it's a calculation of a completely random placement of your chromium atoms in your FCC 100 surface. And this is how it looks like with 15%. You can see that the chromium atoms, just by random placement, will already form this filamentous type of clusters. And if you look at it, the size of the clusters as a function of composition, you can see if you go over 15 to 20%, you start to have very long connected chromium clusters and structures already. And we do think that plays a role in promoting corrosion resistance, formation of chromia above this concentration. So let me lay it out. We have a competition between the thermodynamically stable preferred chromium oxide and the kinetically favored nickel oxidation, which is generally attributed to lower nucleation barrier because of epitaxy. Nickel 100 has an oxidation via chemisorption. Chromium 100, which is actually a BCC structure, has oxidation via subsurface oxygen. Very different animals. Okay, let me show you how that looks like. Where am I with time? Okay, let me show you how that looks like with the STM. So these are all STM images, a tungsten tip. We oxidized with the amount given here. So this is very homeopathic doses. So we want to look at the starting point. So you just add 7 Langley here. This is the nickel chromium alloy, 12 weight % chromium in this one. And you can see there's some curvatures here which come from screw dislocation in the substrate. So you start oxidizing and you see two populations. One are these clusters, which are on the terraces, and the other one is this step edge decoration, which is very nicely crystalline, very specific structure. And if you continue to grow the stuff, you can see the formation of these superlattices. You see a lot of different reconstruction and surface oxides come up. Let me point out that there is a zoo of surface reconstruction. We've seen at least 7 different ones, and only one of them were we able to identify. So if you're a theoretician, please go for those. They're very keen on understanding them better. So this is one of the reconstructions which we don't fully understand yet. So if I compare that to nickel 100, for nickel 100, you need 400 Langmuir or even more to form nickel oxide on the surface, because it's kinetically hindered. Nickel 100 forms a surface reconstruction, which has step edge faceting. So nickel, the surface reconstruction, where the oxygen adsorbed gets rid of kinks at the step edges. And that delays the nucleation. If you put in even traces of chromium, you retain the kinks at the step edges and you start nucleating nickel oxide. So this is kind of the first catalytic type effect or structural effect which you have by doping and going to an alloy from the pure nickel phase. That has consequences because you actually don't want to have the nickel oxide, you just want to have chromia ideally. But you really compete in these very early steps. So why do I know we have nickel oxide? The reason we do is because this superlattice, which you see here, unfortunately not atom, this is a superlattice with a period of several nanometers. This is a superlattice which forms between the registry, between the nickel and the nickel oxide. And it's a 6x7 superlattice, 7 unit cells from the nickel, 6 unit cells from the nickel oxide. That's how we recognize it, and it grows like weeds. So we've solved one question. We know the nickel oxide forms at the step edges and then just grows over the terraces like crazy. Epitaxy clearly favors the nickel oxide. How do we know the clusters are actually chromia? If we heat this one, we reduce the nickel oxide, only the clusters are left. If we add more and more oxygen, we will get more and more chromia on the surface. The clusters are pre-chromia chromia material, and they kind of collapse into a wide range of surface reconstructions. You can do some statistics on them. You can see them ripening here. So these are really nanometer sized clusters, which are kind of more like pancakes than like round layers. Add more oxygen and they will form surface reconstructions and surface oxides. So we now know the nickel oxide forms at step edges, and it is favored because I have chromium in my system. It's very weird, isn't it? The chromia forms first as clusters and then starts to kind of go through several steps in forming our desired chromia. Okay, so I told you all of that, but I also promised you to show you some heterogeneity. And the heterogeneity is not just compositional, it's also electronic. So we have scanning, tunneling, spectroscopy information here, which tells us essentially the position of our band edges in the oxide, of the Fermi level within these band gaps. And we can have structurally identical regions like 4 and 1, for example, but which are electronically different. So this takes out the idea that the Mach potential is the same everywhere and we can't just deal with it globally. We can't, because the Mach potential, which drives the kinetics of our oxidation, differs from position to position on our surface. So the local variation is most likely modulates the oxide layer growth when we kind of move further on into the Cabrera-Mach kinetics regime. Okay, let me summarize all of that. There was a lot of detail, so let's just zoom out a little bit and go into the bigger picture. How does it now work? We start with a clean alloy. We form oxide clusters, which are chromia, oxide, pre-chromia clusters. We form nickel oxide around the terraces, which is promoted by the presence of chromium. Nickel oxide goes laterally, and we have a chromium 100 oxygen terminated reconstruction, which we see here. So what we have is we form chromium pools, just BCC chromium, which is now terminated with oxygen. So you can see there's a lot of motion within that surface. So the surface dynamics is really something which has not yet been captured, but is critical to how this oxide builds up as we go on. The other thing which is kind of nice, we can see the start of the second layer of nickel oxide forming here. So you can see the groove sites in this superlattice are the preferred nucleation sites for the next nickel oxide layer. Okay, so this is a lot of information from STM studies. Let me point out, we don't have the answers for everything. And the reason is the complexity of this oxidation system. And that has also been seen in STM observation of steel oxidation. Or the observation of in aqueous corrosion with some electrochemical STM probes. I would like to step away now from the question of the structural and electrical issues which work out in the STM scale. And I would like to switch now to look at compositional questions. And for that reason, I'm going to use XPS, a wonderful, wonderful method to look at the chemistry itself. How does it play out over time? It's very hard to do fast measurements in STM, but with XPS, you can now use ambient pressure XPS to look at the evolution over time. And that's what we did. And for this purpose, we used bulk samples with specific different compositions, but also different crystallographic orientations. So we average over those. And that's important to remember because we've done recently experiments which show that you can have up to 30% different weights of the oxides as a function of crystallographic orientation. So what we do here is we start with a clean surface, always a good thing. We get that clean surface by essentially heating the whole thing to 700 Celsius, at which point in vacuum, your really, really crappy oxide, which you create in ambient conditions, is reduced in UHV, and we can start with a clean surface. And then we grow the oxide layer by exposure to oxygen. Let me point out that in nickel as well as on chromium, you immediately move into a dissociation of the oxygen, so we don't have to consider a molecular adsorption in this case. You have a clean surface, the nickel 2p and the chromium 2p peaks are shown here, just so you have a starting point. Keep those in mind when we start to go crazy. The other thing you have to keep in mind, which differs from catalysis studies with ambient pressure XPS, is that you start with the information depth. You start to move out of your alloy. You move farther and farther and farther away from your alloy oxide interface. So also keep that in mind when we look at the growth. There's also a lot of information embedded in these specific experiments, which means you experiment for 3 days and then you analyze for, years, whatever data you got here. The first part I'm going to do is I'm just going to separate the signal I have from my metal and the signal I get from the oxide. And I don't differentiate initially kind of, is it oxide or is it spinel or whatever it is. Let me point out that we have never seen a spinel component, which is a mixed nickel and chromium oxide, so that it really facilitates the analysis, fortunately. Okay, let's get started and look at the results. So these are all the alloys we used, 3 binary alloys and 1 ternary alloy where we added 6% tungsten, 10 to the -6 millibar during the experiment. So you don't want to be too fast, you still want to see what happens. 500 degrees Celsius, which really is the regime where the 2 oxides battle it out. Okay, So here is also, you know, my snippet of aqueous corrosion. We've done some work which is specifically also the first review written by Katie Qualina is very informative if you want to have a good overview over what tungsten and molybdenum actually do and how beneficial they are in an aqueous corrosion experiment to the performance of the oxide. It's like magic, you know. The question is, where does the magic actually come from? And a lot of the work I'm going to show you in the next few slides is about to be submitted to Nature Materials Degradation. Okay, so what happens here? Let's look at the nickel-15 chromium first. Oxidation time from the top to to the bottom of this graph. You see here the alloy, the nickel peak for the metal. You can still see that even towards the end of the oxidation. You see a lot of oxide here coming up as you continue the process. About 20 to 25 spectra. We oxidize for 4,000 to 5,000 seconds, which is the same amount in Langmuir if you prefer a fluence unit. If you look at the chromium, you pretty much lose any chromium signal from the alloy immediately, very, very early in the process. So you essentially use all the chromium which is stored in the immediate subsurface layers of your alloy. So all the chromium you have then at that moment to make the oxide comes either through diffusion, through grain boundaries, or very rapid transient diffusion from the bulk of the system. So let's go to the next part. Let's look at how your alloy signal decays and how your oxide signal comes up during the whole process. And what I've shown here, this is just so your brain gets scrambled a little, is I showed all the others we studied. All the closed symbols are binaries. All the open symbols are the ternaries with 6 weight percent tungsten. That's about 3 atomic percent. 2 experiments, 500 degree and 400 degree centigrade. So if you look at the oxide signal, and this is the complete oxide, okay? This is the nickel oxide and the chromium oxide and the tungsten oxide added up together. So you can see that the more chromium we put in there, the more rapid your oxidation happens. This is the nickel 30 chromium, and it's even more rapid if you add a little bit of tungsten. Look at the open symbol here. The oxidation with the nickel 15 6 tungsten at 400 Celsius looks pretty much like somewhere in nickel 15 and nickel 30 chromium. Let me show you one of the, before I do that, let me just summarize. It's hard to capture the full information depth within these graphs, but just looking at them for a few seconds. None of the oxides grow in a layer by layer growth mode. They more or less have strong to weaker island growth modes. The alloys are rapidly depleted in chromium. So all the alloy signal is essentially just nickel. And the nickel 15 chromium at 500 degrees Celsius resembles nickel 30 chromium much more than the other, the binary counterpart. You can now take the next step in the analysis. You can resolve the composition of the oxide, or you can also look very specifically and fit all of the nickel, chromium, and tungsten peaks. And we did all of that, but I'm just showing you here fit of the nickel spectrum. And we followed here the prescription by Biesinger and Payne laid out in their papers. So we really do a very constrained fit here. We use 5 peaks, but we always need to add, in this case, for the nickel oxide in all of these binary alloy oxidations, we need to add 1 additional peak, which is generally attributed to the nickel 3 plus peak. And this is pretty much that contribution is constant throughout the growth of the oxide. So these are defect states which are present in the oxide, vacancies, chromium doping of the oxide, some tungsten maybe in the oxide. And this is a very characteristic for oxides which are grown on binary alloy systems. These are vacancies which are interstitials which are needed to continue the oxide growth, because you need transport through the oxide. So these defects are built in very, very early in the process. So let's take the next step. And let's not just look at how much oxide do I accumulate over time, but let's resolve it compositionally. So that is done here, and I have just 3 examples here. Nickel 15 chromium. So you can see this is all the oxide curve I showed you just now. I'm sure you remember the details. You have the nickel oxide, the open symbols, and you have chromium oxide, chromia here in the closed symbols, filled symbols. So chromia forms very early. You remember these are the little clusters which hang out on all the terraces, which I showed you in STM. However, it does not continue to grow as fast. The nickel takes over. You run probably also out of chromium supply from the bulk, and the nickel oxide will overgrow the chromia. Therefore, the chromia signal is damped over time. If you have nickel 30 chromium, much more chromium is available. You will dominate, the whole oxide is dominated by chromia, and you have some nickel oxide, which nonetheless forms on that particular surface. So the competition is not only into the thermodynamically favorable chromia, you still have nickel oxide hanging out there. The really weird thing, same oxidation conditions happens if you use a ternary. If you use a ternary, you only have chromia. At 500 Celsius, you only have chromia. No nickel oxide will be formed in this particular oxide. And we do think that this is partially, at least, responsible for the excellent performance of this oxide. It's also something you see in aqueous corrosion. It's not quite as pronounced. And if you look at the peak, the chromium to P fit, it is exactly like a chromia solid you use for reference. So let me summarize that. Chromia forms rapidly and overgrown by the nickel oxide. Nickel oxide formation is completely suppressed for the ternary. The high quality chromia is formed. No spinel is seen in any of these examples. And at 400 Celsius, you can see that tungsten is integrated in the oxide layer, not at 500 Celsius. We do think that the tungsten is actually embedded at the interface between nickel oxide and chromia. So why? Why does this happen? I mean, it's so massive. This is not just a percent effect. This is very dramatic. So 2 explanations come to mind. Either something happens in the bulk if you add tungsten, which promotes massively the diffusion of the chromium. So you don't run out of chromia and you move into the thermodynamically preferred pathway. Or the chromium oxide nucleation is promoted at the surface by having tungsten and molybdenum there. So what do you do to interrupt your diffusion? You go to lower temperatures, and that's what we did. So this is at 200 Celsius, and for the sake of full disclosure, this is actually with molybdenum. Molybdenum does the same thing like tungsten, just a little less. So if you look here at the comparison, this is the oxide signal, just integrated oxide, dominated by chromia for the ternary. And if you look, the nickel 30 chromium, this is the chromia, this is the nickel oxide. If you look at the nickel 6 molybdenum, you see that it's very, very similar to the nickel 30 chromium, but not to the nickel 15. So this graph shows how the tungsten is embedded here. I'm not going to go into this one. If you want to have the details, send me an email. I will respond to that and clarify this particular analysis. We can summarize this one. Even at low temperature, even with molybdenum, you see that preference. We have found in the literature no indication that you will have massively faster diffusion if you have a ternary. It can be that it's just grain boundary diffusion, and we need to compare that to single crystal materials, how that plays out. However, at 200 Celsius, nothing moves here anymore. I mean, that is really a very, very sluggish motion within the bulk. So let me give you an additional idea what can happen at the surface. And that goes into the question how the surface chemistries are changed by moving between different alloys. And we saw that with the chromium in the nickel already. And now if we add tungsten, we do think that the binding of our ternary alloy, the addition of that one, moves the system into the preferred thermodynamically, in this case, not thermodynamically, but preferred adsorption site. So the binding energy of oxygen between tungsten and chromium is much higher, much more favorable compared to all other positions on these surfaces. And this was a calculation done by my colleague Leni Arnedotter here. And you can read up on her work on how binary surfaces kind of react with CO in this case. So the oxygen lexes it on that tungsten chromium side. And we do think that the tungsten helps in kind of shuffling, funneling the oxygen into bonding with chromium compared to bonding with nickel. And we do think that this is a significant contribution to change the behavior on that alloy surface. That does not make the problem we posed in the beginning any easier, but it adds a dimension which we think we have to integrate into the consideration of alloy passivation. And it also could give us other ideas about surface treatment. So let me summarize. If you think in surface science and catalysis, you have pressure gaps and you have material gaps. I think we have to add two other gaps, which kind of have to be overcome if we want to get a full understanding of these mechanisms. That's an environment gap. The question of compositions of our gases. Oxygen is not complicated. Adding water changes the game entirely. And we also have, so we have pressure, environment, materials, and we have something I would just call a complexity gap, which means we have to, I think, work more and more with these technical alloys in our studies of surfaces and complement that with using single crystals or very large polycrystalline samples, large grain polycrystalline samples. So let me summarize. Surface science studies can isolate critical aspects in corrosion and oxidation. They enable a deeper mechanistic understanding. However, it's not fully understood what this complexity of a real technical alloy adds to the system and our understanding of it. We would like people to think more about the fact that you have some kind of catalysis or promotion by using not binary alloys, binary reactive alloys, where both components can react. And we would like to put out here for the discussion the catalytic effect of minor alloying elements, or even lower concentrations where you go below 1% with an additional element in the alloy, which can change the game. The question is, can we predict what happens there? Not yet, but there is a vast amount of literature on where people have tried so many different things that we can use that really to stand on for our future work. Can we rightfully call it a catalyst? I hope so in the future. Let me point out that NSF chemistry does not subscribe to that view yet. So I hope we can convince them that this is something which kind of falls under the umbrella of catalysis, just in a very, very different system. Let me thank all the students, all the colleagues, all the collaborators which have worked with us over the years at Brookhaven National Laboratory, and also do very recent XPM work at Lund, which I have not shown here. The people who give us the money, like the NSF Division of Chemistry and DMR, the Office of Naval Research, and some other smaller funding sources from the University of Virginia. And with that, I'd like to close. I hope you at least got some prompts on how to think about different things which you might not have considered previously, and to kind of, yeah, I hope this inspired you in some ways. And I will hand it back to Heather now to guide our discussion of the topic.
All right, thank you, Petra. I'll go ahead and take over the screen. What I'll do is I'll give everybody a little bit of a time while I share my screen to type in some questions for you and see if we have any coming in. So let me go ahead and take the screen from you. We'll do some closing slides, give people a chance to type those in. So let me click over here. And I want to thank everybody for joining us. Today's e-talk was linking dry corrosion and catalysis. Can surface chemistry influence corrosion pathways with Petra Ranke. Thank you, Petra, again for presenting all this material for everybody. I know everybody's getting close to the holidays, so I want to thank everybody for joining us today.
Yeah.
And
I think it was a pleasure. It was a great opportunity to give this talk.
Definitely.
I really enjoyed it.
Well, thank you. And I'd also like to thank our event sponsor, Hayden Analytical, for providing some support for this event. And then I'd also like to remind everybody we have some online events coming up in 2022. This e-talk was our last online opportunity for 2021. So we are closing out the year, and we appreciate everybody's time. Check out the short courses we have coming up. Registration is open. We also have an e-talk coming up at the end of March in 2022. And in between the short courses and e-talks, we also have some webinars on one in January and one in February. Registration is open for those. And upcoming conferences between March and June: FCMN, ASD, ICM, CTF, ALD, ALE. They all have their own individual websites. You can also check them out on the AVS events calendar. We have details becoming more and more available for each event. So check them out. Membership, AVS membership is an annual based membership for 365 days from the day you register. So check it out. It gives you access to our publications, professional career development, technical resources, and discounts on various events listed previously. And you can go to our website, avs.org, or speak with Angela Klink, who's in charge of our member services. And finally, we do have an evaluation coming up as you log out, and or via email will be supplied to you. If anybody has any questions, please ask them now.
I have one in the chat from Catherine Perrin. And she asked whether we've thought about a reverse surface moly or tungsten with nickel add atoms. That's a really interesting question. We actually have not thought about that. And the reason is we were so focused on the technical alloy. So we always started with nickel chromium. But I think it's a really good idea because it offers you, the complete picture in the competition of the adsorption. And I think it's easier to do that in DFT and start with that. But she's right that using different types of surfaces spiked with different atoms will definitely allow you to complete that idea and, hone your skills in predicting and understanding those surfaces. So.
All right. Are there any other questions from anybody? Also remember, Petra's email is also here on the screen. So if you do have follow-up questions, you can still reach her. We're happy to keep that line of communication open.
Yeah.
Um,
No, and I realize these are a lot of different data sets. So it's hard to capture all the details. I'm more than happy to answer more questions.
all right. Well, I don't see anything else coming in, so we'll go ahead and thank everybody once again. Thank you, Petra, for presenting the information for everyone, and we wish you all a happy holiday season. Please stay healthy and safe, and we hope to see you at some upcoming events in 2022. And thank you for joining us, and we'll see you next year. Thank you again.
Yeah. Thank you, Heather, and all the support team. It was a joy to work with you.
Thanks.
Bye.
Bye.